I'm going to describe a type of neural network called a convolutional neural network, and convolutional neural networks are very useful and very successful in computer vision. We've discussed how a neural network has many layers, and each layer consists of many nodes. And each node is its own little computational unit. It performs its own little computation. In a convolutional neural network, some of the layers are what's called convolutional layers. And in a convolutional layer, the nodes are what I'm going to call convolutional nodes. And I want to describe the calculation that is performed by a convolutional node. In this picture here, we're looking at the architecture for a particular example of a convolutional neural network. And this first layer is a convolutional layer. And it looks like this layer consists of 6 convolutional nodes. Each node has a kernel, and it has a bias term, which is a scalar. So it has a kernel and a bias term. And the computation performed by one of these convolutional nodes is it takes this array as input. It performs a convolution using its own kernel, its own convolutional kernel. The result of that convolution is a two-dimensional array of numbers. And then that convolutional node adds its bias term to each component of that two-dimensional array of numbers. And then each component of that two-dimensional array, after the bias term has been added, each component gets fed into the ReLU activation function. And the resulting array, after the ReLU activation function has been applied to each component of the array, that resulting array is the output of that convolutional node. In this layer, we have 6 convolutional nodes. So 6 of these two-dimensional arrays are the output of that convolutional layer. Next, we have a max pooling layer. And all this layer does is it just applies the max pooling operation to each of those 6 arrays, which were output by the previous convolutional layer. Next, in this neural network, we have another convolutional layer. And if you count this up, this layer has 14 convolutional nodes. Each node has its own kernel and its own bias term. And let's count up how many parameters are there associated to one particular convolutional node in this convolutional layer. Let's think about this particular convolutional node here. It has a kernel and it has a bias term, which is a scalar. And what's the shape of that kernel? It's 3 by 3 by 6. And why is its depth 6? Because the output of the previous pooling layer is an array, a multidimensional array, which has depth 6. And the depth of the kernel for this convolutional node, the depth of that kernel has to match the depth of this array, which is being fed as input to this convolutional node. So the shape of the convolutional kernel, the shape of the kernel that belongs to this particular convolutional node is 3 by 3 by 6. So the number of parameters that go into that one kernel is 3 times 3 times 6, so that's 54. This node also has a bias term. So that's one more parameter that belongs to this node. So that means this node, this convolutional node, has 55 parameters. And in this convolutional layer, we have 14 of these convolutional nodes. So 55 times 14 is the number of parameters that go into this convolutional layer. Next, we have another max pooling layer. All this layer does is apply the max pooling operation to each of the 14 arrays, which are the outputs of the previous convolutional layer. These 14 arrays that we see here are the output of the max pooling layer. What happens next is that these 14 arrays are flattened to make one big vector, and that vector is then the input to a dense layer. So we have this dense layer, and then we have an output layer. If we're doing multi-class classification with k classes, then this output layer is going to have k nodes, just like we're used to. The output of this final layer is going to be a list of k numbers and a vector with k components, and that vector is going to get plugged into the softmax function. The softmax function will give us a probability vector, which tells us the probability that the image that we're looking at belongs to each of the k classes that we're considering. Let's implement this particular neural network architecture using TensorFlow and use it to classify MNIST digits. So here we are importing TensorFlow. We're reading in the MNIST data set. We are normalizing the data. And now here we are building our neural network. We're telling TensorFlow that the first layer is going to be a convolutional layer. It's going to have 6 convolutional nodes. Each of these nodes is going to use a 3x3 kernel, and the activation function is going to be the ReLU activation function. The shape of an input to this layer is going to be 28 by 28 by 1, because that's the shape of an image in the MNIST data set. And then next, we're going to have a max pooling layer. And then next, we're going to have another convolutional layer. This convolutional layer is going to have 14 convolutional nodes. Each of those nodes is going to use a 3x3 kernel. The depth of that kernel is going to be equal to the depth of the array that is being fed into this layer as input. The input to this layer is going to be an array whose depth is 6, because the previous convolutional layer had 6 convolutional nodes. So that means that each kernel in this layer is going to have a depth of 6. And then next we have another max pooling layer. Then next we have a max pooling layer. And then we have a flattening layer. And what this layer does is it just takes the output of the max pooling layer and it flattens it into just a vector. And then that vector is fed into a dense layer with 64 nodes. And then our final output layer has 10 nodes because there's 10 categories in this classification problem. So that's the architecture for our neural network. And now in this line, we are compiling our model. And when we compile, in this compilation step, we tell TensorFlow that the optimization algorithm to use when training this model should be RMS prop, which is similar in spirit to stochastic gradient descent. The loss function that we should use is categorical cross entropy. That's what we always use when we're doing multi-class classification. The metric we're going to keep track of during training is just the classification accuracy. So let's run this section of code. Then we have to do a little bit of processing on the data to put it into the form that TensorFlow expects. And then we are ready to train the model. So we're going to use 5 epochs, and we're going to use a batch size of 64. And let's go ahead and start training the model. So this part is a little bit slow. I'm not running this on a GPU. If we were doing this on a GPU, it would be way faster. But this is just running on my CPU, so it's pretty slow. So we finished training the model, and now let's check how well our model performs on the test data. This also would be faster on a GPU. Okay, let's look at test at, okay, 98.5% accuracy. So we have 98.5% accuracy on the MNIST data set now. That is not bad. It's definitely better than what we got with logistic regression. We got 92% accuracy with logistic regression. We'll be able to do better than this with a different architecture, but 98.5% accuracy is not bad. If we type model.summary, then TensorFlow gives us a useful summary of our model. So TensorFlow is telling us that we have a convolutional layer and the number of parameters in this layer is 60. Then we have a max pooling layer. Then we have another convolutional layer. This layer has 770 parameters. Then we have another max pooling layer. And then we have a flattening layer. And then we have a dense layer with 64 nodes. And then finally, we have a dense output layer with 10 nodes. Notice, let's look at this number 770. This is 770 is equal to 55 times 14. That's what we got earlier when we were counting for ourselves the number of parameters in this layer.